Okay, thanks for everyone's time today. I'll start with just a few summary slides to give you some positioning on the Ansys Discovery technology, and then Tim's going to give you a live demo. I think a reasonable proportion of the people who had signed up the registrations were SpaceClaim knowledgeable people, SpaceClaim aware people, and so you may have heard something about this product before. There was a forerunner called Discovery Live. And this name, Ansys Discovery, replaces that product. And for those of you familiar with SpaceClaim, you'll recognize elements of the user interface. The geometry side of it is powered by SpaceClaim, or is SpaceClaim. And what was Discovery Live is a real-time GPU solver that's embedded within the geometry system. But whereas before, you had to go to another product, which was called Discovery AIM, to do high fidelity physics using the traditional simulation process of meshing and running simulation. Ansys have delivered that functionality into the same single user interface. So within one interface, you can do geometry modeling, real-time GPU solving, and high fidelity mechanical, fluids, thermal, modal analysis all in one system. It's a modern user interface from our perspective, and it's got the ease of use of SpaceClaim. And obviously, Tim will be demonstrating it. So next slide, please, Tim.
Slug.
And no, just press again. Next thing will come across. So as I mentioned, if any of you aren't aware of SpaceClaim, it is what's called a direct modeler. So that's different from a feature-based modeler that you might find in traditional CAD tools like SolidWorks or Inventor. Direct modeling is well known for being very good at manipulating geometry of self-generated geometry or external imported geometry from virtually any format, whether that's solid, surface, or mesh data. And of course, SpaceClaim utilizes direct modeling, and that's what the Discovery product also utilized to either help prepare the models for simulation. So if you are going to simulate your geometry, particularly via the high fidelity simulation, the consequences of the geometry complexity and the associated mesh need to be considered. You may need to de-feature your geometry to economize on the mesh and the simulation runtime. Slightly different with the GPU modeling, which if you press the button again, Tim. So this is what we term the exploration side. So Ansys have rewritten its simulation capabilities to run on graphics processing unit. There is the requirement that you have an NVIDIA graphics card on your machine. So Tim will be demonstrating utilizing a GPU NVIDIA graphics card, and that runs the simulation. We've been told later in the year there's going to be the option for sourcing that out to a cloud implementation. So if you don't have dedicated NVIDIA GPU, you can still get a result back from the GPU processing. And obviously what a GPU offers is typically a lot of available cores. So, on your typical CPU, your PC, you might have 4 cores, 6 cores, 8 cores. Whereas on a GPU, it's pretty common to have 500, 1,000, 2,000 cores. So that's giving the sort of expansion of processing capability. And because simulation is a pretty good process to parallelize, then 1,000 or 2,000 cores is a great environment for speeding up significantly the runtime results to be returned. If you press the button one more time, Tim. The verification stage is using the high fidelity physics that I've referenced. So Ansys's main 2 flagship tools are Ansys Mechanical for finite element analysis and Ansys Fluent for fluid flow. And in essence, the results that are available within the verify mode of Discovery are powered by those 2 systems. Thanks, Tim. And can you just press the button twice, I think it is? All right. So the reason Ansys is doing this, a couple of reasons. Ansys is typically used at the high end of the marketplace by simulation experts. And simulation is often found to be used maybe for verification or towards the end of the process. maybe just before product testing, physical product testing, but often after design or development has occurred. The cost to modify a design if a defect is identified through simulation can be significant. And so, the long-held understanding that if you can move simulation up front, you potentially reduce that cycle of increased defect modifications, or potentially if you can use simulation to drive your design, you're potentially going to come up with a better result or a better final design or early design, and you've got more flexibility to change the design. So the challenge is that the simulation experts aren't always the people who are doing the conceptual design. So it may well be the designer, the conceptual design person, the project managers. And so the aspect of coupling this in a design tool like SpaceClaim, and one that's very easy to use, is obviously the agenda for expanding the people who can use simulation and to use it upfront. That's the reason Ansys are doing this. So it's a design-focused implementation of simulation. Next slide, please. Its capabilities in the GPU mode covers structurals, fluids, thermals. It does generative or topology optimization. It does modal analysis as well. Tim's mostly going to concentrate on showing you how to set up a structural problem, but we will quickly run through, if we have time, and just show a quick fluids example, thermal, and a topology optimization as well. But we won't set those up. It is pretty quick to set up any of these problems, but again, I think you'll get the idea from the structural example that Tim will go into in a bit more detail. Next, Tim, next slide. So again, just to summarize how this works, you'll see Tim in two modes. The screen might be a bit small for you to see, but there's on the left-hand side, there's the text says Explore in the bottom tab, and on the right-hand side, it says Refine. And those are the GPU Explore mode or the Refine high fidelity meshing and physics modes. So Tim's going to show you how quick GPU processing occurs, which will typically give you a result within seconds. And then the high fidelity result will take a little more time, a few more minutes in order for a result to be obtained. But the accuracy of this is, top of the market, FEA or fluid calculations if you need high fidelity results for whatever reason. Okay, over to you then, Tim.
Okay, cheers, Peter. First of all, can you see my screen?
I can indeed.
Perfect. Okay, hi guys. So as Peter mentioned, we're going to be looking at this software that you can see right now, which is the Discovery software, and we're going to be going through a structural simulation through the Explore stage and the Refine stage, which is the high fidelity meshing stage. First of all, if I click in this top right left-hand corner and click the home page, we can open models from here. Obviously, we can use search for models. We've got our recent files and we've got sample files. Sample files are great for just already set up thermal, fluids, structural, different types of simulations. What's also nice is this learn stage. You've got your welcome screen, which everyone will see straight away. And this is a little video and basically just tells you how to use the software. And you can also go through an interactive tour of a structural and a fluid flow simulation to get you started, and links to the forum and online tutorials, so that's great. I'm going to just double click on this model, because this is the model we're going to be looking at. And this is just going to import the geometry. Also, we can import most CAD formats. Most CAD formats we can import, so you won't have any trouble actually importing data from different CAD tools. But this is the part that we're going to look at. At the moment, it's just coming as CAD data. We haven't got any physics set up on it. The first thing that we're going to do is just to quickly give you a bit of an overview. People that are familiar with SpaceClaim will be familiar with these tools, but these are basically your modeling tools. We can actually model inside here, either create and edit the geometry we've got. We've got a facets tool, which basically just allows us to work with faceted data a lot easily. Display tab. Straightforward, just changing colour schemes and that sort of thing. Measure tab and a prepare tab. Prepare tab is a great tool. There's loads of tools in here for basically prepping your model for analysis. Some great tools in here, things like volume extract for fluids. And these tools allow you to repair a model if it comes in, it's not a solid body. But the tab that we're going to be spending most of our time in is obviously the simulation tab. In terms of the UI, we've got our model tree up here, and we can see our components and things in here. And this is our physics tree. So as we populate and add things, we'll see it appear in our physics tree. At any point, you can hit the F1 key, and this is an interactive help tool. So if I hit the F1 key now, we get a interactive help tool. And basically, this will tell you what everything is. And as I hover over certain things, you'll see the interactive help tool actually changes, and we can see what that is. So we can hover over things and get a little bit more detail on what they are. So whenever you're stuck or you want a bit more information, you can hit that F1 key, and that'll basically show you what you're looking for. We're going to add a structural simulation. So the first thing we need to do in this model is actually add some fixed supports. So the fixed supports I'm going to add are to these like metal pieces, metal brackets, and I'm going to add them to these holes. So to do that, we can click on a hole. This little icon pops up, and we can look for a fixed support. If we hover over them, we can see what each of these do. Obviously, I don't want to select them all manually, so we do have a power select, and this is a tool that's been carried over from SpaceClaim. But this basically allows us to search all the bodies and select all the holes equal to 5 mil. So I want all these 12 faces added as fixed supports. And we can see here, we can actually choose different types of supports. But actually, in this instance, I do want them to be fixed. So I'm happy with that. Hit the tick box. And hit escape twice just to close this bar at the moment. Hit escape, and that'll just close what we've got in front of us. As we add things, we'll see things appear in our tree. So we can see the fixed supports have appeared. We can also see gravity conditions appeared, but it actually is excluded. I'm going to keep it excluded for the time being. And we've also got some contacts up here. In the explore stage, contacts will be bonded. And this is using the GPU, so it is automatically assumed that they're bonded. We have heard that soon in future releases there will be actually contacts added in the GPU stage as well, but you can add contacts in the CPU stage. So we've added our supports. The next thing we're going to do is add a mass, and I want to add a mass to these two faces. So I'll hold Control to select them both. I'm actually going to minimize this as well. And again, click on this little interactive bar into my structure, and you can see I can add a mass there. We can add a value, which I'm going to add 5 kilograms. The mass location at the moment is identified by this blue sphere. And I actually want to change that point, so I can click on this use remote point, and I want to change that to 0. And as I modify it, you can see this sphere change position, and I want this to be 200 millimeters. And the default units at the moment set to meters, but obviously I can type in mm and we will get meters. And we can see that's our new remote mass location. So if I'm happy with that, again I can click and hit the escape key. And anything we want to modify, again you can do it from the physics tree. So I can double click just to bring this area back up. I can modify the actual mass from here as well. Also, when you're creating a solution, it's just presuming that the material that you're using is structural steel. So it's presuming every single part of this is made of structural steel, but that is very, very easy to change. So let's say, for example, these straps are going to be made of a different material. So using a triple click, which basically allows me to select the body, I'm going to triple click on both of these bodies. Again, using my little interactive bar. This is the material icon. And I can basically search for a material, click other, and let's say, for example, I want to add iron or aluminium. I can basically type in, and you can bring up the material that you want. You can modify any of these values as well, and you can create your own materials. Also, Discovery has got access as a module to Grantor materials, which is an additional module, but that's a massive library of materials if you're big into material science. So just thought I'd mention that. So what we can see now is that we've got two materials added. We've got structural steel for the main part, and then these two parts in a slightly different colour, but that's added. What we're going to study is a structural simulation. We're going to study a modal, so we're going to turn on natural frequency. And this little bar area down here in the middle of the screen, at the bottom, you can see me circling it. This is what we call our SID, our simulation information display. And again, I've just hit the F1 key, so you can see as I hover over something, hit the F1 key on that tool, it gives you more information. And we can see that we're doing a modal simulation. Obviously, it's a structural. We also have a little information bar, notifications these are. I'll just hit the F1 key again. We can see our notifications. Basically, it's showing you what's going to be ignored. So this is a really useful thing. If it's giving you errors, it will basically highlight where those errors are. We're going to now basically start solving this simulation. So I'm going to hit this solve button in the right-hand corner. It's a little green solve button. Hit this one, and instantly we'll start solving it. The fidelity bar is down here, so I'm going to use just a lower fidelity for demo purposes, but you can increase this bar to get more accurate results. And again, this is using, as Peter mentioned, an NVIDIA graphics card. And I'm not sure the RAM of my graphics card, but the more graphics RAM you have, the more accurate and quicker results you're going to get. So if you've got a massive 16 gig graphics card, you're going to get quicker results. As it's converging, you'll see this little white bar follow around this green hexagon, and that's basically saying that the results are converging. We will have results in but not all the results yet. And when it stops, that means the results have converged. So we can see that's nice and green now. And we can see, obviously, our graph on the right-hand side. At the moment, we're looking at displacement and we're looking at first mode. If we click this, we can show 6 different modes. In the GPU stage, you can only look at those 6 modes, but if you want to look at further modes, you can go into the CPU stage and study different modes. But yes, so we can look at the first mode, and at the moment we're looking at displacement. We might actually want to animate that displacement, so we can click on the deformation tool down here, and we can see the deformation, and we can animate it if you want. So we can see that deformation animating. If we pause that, we'll go to a different mode, let's say mode 4, and we can see the deformation there again. And again, hopefully you can see that all the contacts are bonded. We can look for different things here as well. We can look for stress, and we can add our own values in these, the top and the bottom values. And using this tool here, we can also show min-max locations, just to highlight those locations, and we can drag this down to get a bit of a better idea of the higher stress points. So that is basically how easy it is to set up an initial simulation and actually get results very, very quickly. So this is in the explore stage. So that was just hopefully showing you the setup and actually solving a solution, a modal solution in this instance. So what I'm going to do is just pause that simulation and turn off the results, but you also do have different results, obviously for fluids, isosurfaces is quite useful, but for this, which is going to be looking at contours. And now we're going to add some more parameters and go into what we call the refine stage. So to go into the refine stage, this is again going to take us into using the CPU solvers. You basically just go right here and click on the refine. Straight away, I could solve this, but I'm going to turn off natural frequency now. And you can see now we can't solve this. This little red bar is indicating that there's no button anymore, green button. It's basically saying we need to add some more parameters to actually get a solution. So the first thing I'm going to do is add include gravity. So I'm going to click on here and say include. And if I double click on gravity, I can see at the moment it's going in the minus Z direction, obviously of 1G. I might want a 2G G loading force in the minus Y direction. So if I change this to 0 and I type in 18 here, I want it to be -18, but you can also change your direction here as well. So I can say -y there, and we can see now that's going in the direction that I want it to. So I've added a 2G load force in the y direction. The next step that we're going to look at is now we're going to look at contacts. So as I mentioned earlier, the GPU stage is presuming all the contacts are bonded. So if I double click on my contacts, I can see in the whole assembly there's 11 contact pairs, and if you look closely, you may just be able to see these little white or yellow spheres, and each of these is basically a contact pair. If I want to start modifying the contacts, I might want to modify the contact between this body, which is the pipe, and the secondary body is the sheet of metal. So between those two bodies, there's one contact pair, and at the moment it's obviously bonded. I might want to change that and say, okay, I don't want there to be any contact there. I want to exclude it. I want to prevent that from the simulation. So I'm going to click this tool here. In reality, there probably would be some sort of contact, and we might add a frictional or a sliding contact. But we can see we can have joints and permanently bonded and exclusion. So for the 3 pieces of metal, I'm just going to do that. Secondary is the pipe, one contact pair, and then it will exclude. And as I'm doing this, you'll see the physics tree on the left-hand side update. So I've added 3 prevented contacts to the pipe and the sheets of metal. I'm then going to look at the straps. So the straps at the moment, so if I click on the body and the strap, body and then the strap, one contact pair between them. If I click this little arrow, at the moment we're grouping the contacts via body. I might not want that. I might just want actually one face to be bonded. So for example, I might just want this front face here to be where there may be a weld is. These side faces might not be actually welded, so I can exclude them from the contact. So I just hold control on these two and say those 2 faces I'm going to exclude. And I'm going to do the same thing for this pipe. Hold control and just exclude those 2. So basically what I'm saying is there's just one weld along the front face. The side faces haven't got any contact. I'm going to change these back to group faces by body, and I'm actually going to remove the contact between the strap and the plate. And I'm going to do the same thing for this one. As I do that, you'll notice my SID has gone red again, so it's saying cannot solve, because obviously if I go to my information bar, it will tell us the error and it will say there's unconnected locations, which is understandable. But I'm happy with that at the moment. What I'm going to now add is a joint manually. So these areas here, I'm going to add a joint manually. So if I double click to my structural, take it to my joints, and I want to fix joints, and the secondary surface is going to be this area, and hit the tick box. So I'm now adding a joint manually between those, and this is again just sort of simulating there might be a bolt there. I'm going to do this for the 4 areas. And it will stay in this joint mode, so that's quite nice. So you don't have to click too many times, you just have to select the surfaces you're interested in. So those 4 have now been set up. They're basically, the simulation is now ready to be solved. The last thing I want to show is just basically adding a local mesh setting. So for some areas, you may want to control your mesh size. Let's say, for example, the strap and these 3 faces. We may wish to have a local mesh setting on these. And I'm going to just put in a 5mm mesh setting, and we can again see this appear in our tree. Just to simplify the tree, I'm just going to minimize these areas. This is ready to be solved. Again, we're in the refine stage now, so we will see the mesh appear, and I'm going to hit the solve button. And this is using the CPU. So as this solves, the green bar, once it gets sort of halfway around, we will be able to turn on our mesh and actually visualize it or show it. So you will be able to see that, but it does take a few more seconds than the GPU stage to actually get some starts, some results. So we should be able to see the mesh now. And our mesh is turned on. The parts that I didn't set a local mesh setting for, I obviously using a global setting. And again, this is just based on this little bar here. We can also modify the global settings up here. But hopefully you can see the areas I selected have got the 5mm mesh, as you would expect. And again, we can see the model converging, and hopefully shortly we'll start to see some results. So again, it wasn't too slow. It was actually quite quick, but it, again, only using a simple demo model, sometimes it does take a little bit longer. Again, on the left, right-hand side, we've got our bar. In this instance, we're looking at stress. So we can always turn on off the mesh if we just want to see our color map. And we again can drag this down to highlight high areas of stress. We can turn on our show min and max locations. And we can also show deformation, again, using this tool here. And we can animate that deformation. And we can also look at areas, stress, displacement, and we can also turn on monitors so we can see here our factor of safety, our max displacement, and our maximum stress as well. So those monitors are there, and they can actually create charts as well for different values. So that is the model basically taken from importing a standard geometry, taking it through the explore stage, which is using the GPU to get results, and then we've taken the model, added more parameters which you couldn't add in the explore stage, such as contacts and obviously our mesh settings, and then we've looked at it in the refine stage and got results again in this stage to potentially validify your results from the explore stage. Hopefully that's given you a bit of an idea of how to set up a simulation and get results. This is just a structural one. I'll very quickly now just show you a fluid one that's already been pre-set up. If I just go into my home page, this is a fluid example, and I'll just say no to that. So this is the fluid example. It's actually a fluid thermal example, and this gives you an indication it's a fluid thermal example. So we can also hover over it. It's a steady state thermal fluid flow. If I hit the solve button, we'll start solving this part. At the moment, we're just looking at our streamlines, and I can section this model. So at the moment, we're just looking at streamlines, and we can modify these to suit. I might want to turn on my contours and turn off streamlines, and we can see this here. And we can also section it using this cut tool, which will allow us to cut through the model where we wish. So this, as I say, this is a fluid flow. Again, on the left-hand side, we can see our physics thing. We've got a property of air. I'm just going to move this grid down a little bit. And you can see our setup on the left-hand side. So we've got a temperature going in one of the outlets of 22, for the other outlet was potentially 5. And we can start to see things on the left-hand side, again, temperatures, pressures, and that sort of thing that we'd expect to see in a fluid simulation. Again, this is using the explore stage. If you wanted to move on to the refine stage, you could take all this stuff into the refine stage and then add your mesh properties. One last one to show is the topology optimization. So again, topology optimization is this one. If I go into a sample file, we may be able to actually simulate one. So a topology optimization is just set up using your structural setup. So you've got your material, it's chosen topology optimization here, gravity excluded, and we've got our fixed supports, and then we've got our forces added here. So again, very simple to set up. Once you're happy, again, you just basically start the solve button. And with topology optimization, you're basically choosing like a mass, like a reduction target, a mass reduction, or a maximum stress or maximum reduction in weight. And as it's converging, you'll see the model basically remove material. And eventually it will converge on the target that you've set. I'm not sure what the target, this one's already pre-set up, so I'm not sure on the target of this one. Might be like 30% or something like that. But it'll converge. It looks like it keeps going, it's keeping converging. We always show our monitors. If you're happy with the result that you're at, you can basically sort of pause the simulation, and then you can take this result and turn it into an STL, which can then be taken into your CAD software to either back engineer, reverse engineer, or technically you could 3D print it. So just to show you examples of something from start to finish, just quickly open this one because it's already got the results set up. Turn this on. So this is the part that we were, this part here is the part that we're optimizing. If we hide that part, we can see we've got different results based on our optimization settings. So we can see the STL on that part, and that's one of them. Another one is this one, and another one is this one. Once you're happy with your results, you can obviously right click on them and actually create a validation simulation on the results to make sure, again, it's performing to the right specifications, and that'll be based on all the physics that you've got set up here as well. So just wanted to quickly show you those two, but hopefully mainly it's going over structural and giving you an overview of the software and how to import and set up an analysis solution. Is there anything else you'd like me to add, Peter, or do you think I've covered most things?
Just, you haven't really shown any simulation running and then the geometry changing. So I don't know whether you want to run a simple bracket example and change geometry and see how quick.
Yeah. Let me just go to the home page. I'll open that one. So again, this one has already got the physics set up on it. Hit the solve button just to show you how quick we'll get the results. I might look at my stress just to find out the areas of max stress, and again I can drag this down just to find out the max areas. Again, we can see obviously this area here is the area of max stress. Or I can use this tool here, show the minimax. Actually, the max is down here. So if there's an area of max stress, you may then actually want to go in and actually modify the geometry. So these two areas, you might go, okay, that's quite a high area of stress there. So using my design tools, one of the main design tools is pull. We can actually double click on a face, and we can start to thicken these faces. So I might actually say, okay, I want to thicken that by 2 mil. The simulation is now remeshing, and we can see that we have now got a lower area of stress in this area that I thickened. So very quickly, you can actually modify this while the simulation is running. I might even go as far as saying I want to double click this area, which is selected that area. I can even fill in that hole and actually totally get rid of it. And that'll change the model. So you're changing the model dynamically and pretty instantly seeing what effect that actually has on the simulation. So again, a very, very quick example of that. Of just updating models, and these are all using direct modeling tools that are based in SpaceCrane.
And in this example, Tim, the monitors probably showing those 3 changes you made.
Yeah. So that's the factor of safety change from the first, second to third. And again, you just right click and show a chart there, and we can show what changes they make. Obviously. And the last one is there. So each change is a different iteration, and you can see what effect that has from the first one to the third one. So they can be all exported as well into tables. Yeah, is there anything else, Peter, you can think of?
There is parameter studies. I don't know whether you've got an example ready.
I haven't got an example ready of that, so I don't think this is one cell. I don't think any of these have got parameter set up, have they? No,
they have. It's pretty straightforward to set up a parameter study. You basically, again, those of you familiar with SpaceClaim, you can set a dimension as a group entity, and that parameter basically can be looped between a minimum and a maximum with 5 steps or 10 steps or whatever. You can do multiple variables, so you might do 3 variables with 5 steps each, and then run that parameter study. What it does, it runs each simulation result. As you've seen with Tim demonstrating in the GPU mode, most results come back within 2 to 5 seconds. And so if you're running a parameter study with 50 simulation runs at 5 seconds each, you'll get an array of result sets reproduced and presented to you in a couple of minutes, including the ability to look at these parameters against each other. So you can basically see a Pareto front, as it's called, where you're looking at the performance of one parameter versus another. So that gives you the ability to look at optimizing your geometry by driving parameters. And again, to do that within a couple of minutes is probably unique in the marketplace. Most parameter studies will obviously take the length of a normal simulation. If that simulation run is 20 minutes, and if you want to do 50 simulation runs, you've got a long time to wait for the results. Okay, well, we've done about 40 minutes. We're happy to throw it open to questions. I could unmute everyone, or if anyone wants to put anything in the chat box, you are welcome to do that. So let me just check where the unmute all setting is.
I'm just looking at the chat now. I think we've got one question. So you have fluid temperature and material details. Can you calculate the heating profile of the manifold as the hot gases flow through it? Yes, I think that'll be a multi-physics. The answer is yes, you can do that. It will just be a multi-physics setup, so it'll be structural thermal, I believe, which actually I think you're saying fluid. I don't think you can do that in the explore stage. The fluid and also you calculate the heat profile of the material of like the manifold, but you can definitely do that in the refine stage, which allows you to do a lot more different multi-physics. So you can definitely do that in the software, but in the explore stage, I don't think you can. In the refine stage, you definitely can. I think that's the only question. I think, Peter?
Yeah, I can't actually see any chat questions.
Can you not? Okay, so
my interface.
It might be to me privately then. So it
right,
might
gotcha.
Privately. But yes, but the answer to that is yes, you can do that in the refine stage of the software, which is the meshing stage, which gives you a bit more options in terms of your simulations. Potentially in the future, it might be in the explore stage as well. I think that's the only question we've got. So happy to sort of end it there.
Yep.
And say we will have recordings, so if you do want a recording sent out, we'll send all those out and say thanks for tuning in. And if you do have any questions privately, feel free to drop us an email as well.
Let me just add, if anyone wants a one-on-one session with Tim or myself, happy to do that on your data, show you how the software works. As you can see, it's quick to set up problems, so we're happy to do that. If any of you are SpaceClaim customers, we're running a very price-attractive upgrade option for existing SpaceClaim customers to go to Discovery this quarter. Myself or Tim, again, happy to inform you about that sort of implementation, cost implication. Just for your reference, Discovery without the CPU simulation is about twice as expensive as SpaceClaim. But if you're a SpaceClaim customer, you basically upgrade having taken into account your SpaceClaim seat, so it's about the same price as SpaceClaim. And then the CPU mode is depending on whether you need FEA or CFD. That tends to be a bit more expensive, but again, the offers are running at the moment make it about 3 times more expensive than traditional SpaceClaim. But depending on requirements, we're putting pretty good packages together before year end if anyone has an interest. And we'll send out the recording to everyone after the meeting. So thanks for attending.
Cheers, guys.
Thanks for the demo, Tim.